So in 6.4, we're going to be talking about a different way to measure angles. It turns out that this way is the natural way, or a better way to measure angles, and we'll talk a little bit about why I call it the natural way a little bit later. So let's start with our unit circle. So we know that the circumference of a circle is pi times d, which is equal to 2 times pi times r, where r is the radius. This is the distance around the circle. So imagine if you were to start at the point 1, 0 right here, if you were to walk around this entire circle, you would walk 2 pi r units. So for the unit circle, since the radius is 1, that means that the distance around the entire unit circle, or its circumference, is 2 times pi times 1, or 2 pi. So now we want to talk about angles in the way that we have been talking about them. So if I were to rotate from the positive x-axis to this point, I've written down this angle 30 degrees. So now if I wanted to ask a different question, well then, how far did I walk along the edge of this circle? So if I were to go from here to here on the circle, well, how far did I walk? Well, I know I went 30 degrees, and how many degrees are there in an entire circle? Well, we know there are 360 degrees. So then the part of the circle, or the proportion of the circle that I went around, would be 30 degrees over 360 degrees. And 30 goes into 360 12 times. So that means I went around 1/12 of the circle. And we took note that right here, well, what is the distance all the way around the circle? Well, the distance all the way around the circle is 2 pi. So then 1/12 of 2 pi is 2 pi over 12, which reduces to pi over 6. So the distance I would have walked from the starting point to here on the circle would be pi over 6 units. This turns out to be the definition of radians. So the distance traveled on the unit circle is the measure of the angle in radians. So what this is telling us then is that 30 degrees is the same as pi over 6 radians. All right, so radians are a different way for us to measure angles. So we've all grown up using degrees, which we're really, really comfortable with. It turns out in mathematics that radians are the way to go. Otherwise, math starts to get really, really complicated because degrees are a derived unit. And what I mean by that is they were made up by humans to make our life easy. In fact, they were made up by the Babylonians, and the reason there's 360 degrees in a circle is that they used a base 60 number system. And it's completely arbitrary. It turns out that the natural measure, or as we'll see, the unitless measure of a circle for talking about angles, is radians. And it makes the math work out a lot better. So let's go back and look at our diagram a little bit. So we really came up with this idea that we converted from degrees to radians by finding the proportion of the circle. Well, it turns out we can generalize that idea. So if we were to ask, well, how many radians is 45 degrees, we would have the proportion 45 degrees over 360 degrees is equal to the radians, which we'll use the symbol S, so that's our radians, over, well, what was the circumference or the distance around the entire unit circle? Well, it was 2 pi. So this gives us our proportion that we need to solve. So if I multiply both sides of this by 2 pi, but before I do that, let's simplify. How many times does 45 go into 360? Well, that's going to be 8 times. So the left-hand side reduces to 1/8 is equal to S over 2 pi. So then if I multiply both sides of this equation by 2 pi, those reduce out, and we get that S is equal to 2 pi divided by 8, and that reduces to pi over 4. So 45 degrees is the same as pi divided by 4 radians. All right. Here is a U-try for you guys. So how many radians is 270 degrees? All right, so to convert 270 degrees into radians, we would use our proportion 270 over 360 is equal to our angle in radians divided by 2 pi. So multiply both sides by 2 pi, and then we start reducing. So 270 and 360 reduce to 3/4, and then the 2 and the 4 reduce to 3/2, so we get 3 pi over 2 is equal to x. So 270 degrees is the same as 3 pi over 2 radians. So if you take a look at your unit circle, you'll notice that what we were doing is actually present here. So if you look at your unit circle, here's 30 degrees, and what does 30 degrees pair with in radians? Pi over 6. We go down to 270 degrees here, and what did it pair with on our unit circle? 3 pi over 2. So on our unit circle, if we're given something in degrees, we can use the degree ring on the inside, and if we're given something in radians, we can use the radian ring on the outside. And it also gives us the equivalence of some of the common angles. So 30 degrees is pi over 6, pi over 3 is 60 degrees, pi over 4 corresponds to 45 degrees, and so forth. So we've got these values that we can convert in between manually, and some of them we'll probably memorize over time, which will also be helpful. All right, so let's take a look at our next example. So we wish to plot each of the following on our unit circle. So we want to plot a rotation of pi over 4. Well, how much of a circle is pi over 4 radians going to be? Well, what's the entire distance around the circle again? 2 pi, right? So pi over 4, well, one way we could know is that just convert it to degrees. So pi over 4 is going to be 45 degrees. So it's going to be here. But if we did our proportion, what is pi over 4 divided by 2 pi? We'll make it a fraction over 1. So that's pi over 4 times 1 over 2 pi. Pi's reduce out, and we get 1 over 8. So that means it would be 1/8 of the circle. Well, that would be 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8. So 1/8 of the way around the circle would be right here. Okay, how about 2 radians? Well, that one's a little bit different. We can do the same thing. We have 2 divided by 2 pi. And we get 1 over pi. So if we grab our calculator and we approximate 1 divided by pi, 0.31 means how much of the circle are we going to go around? Well, 0.31 would be like 31%, so it's almost a third. So if we were going to divide this into thirds, 2 radians would be about right here. Similarly, if we did the same thing with 4, that's going to be a similar proportion. So 4 over 2 pi would give us 2 over pi. And on our calculator, if we go 2 divided by pi, well, what percent of the circle would we go around? 63%. So 50% would be here, 75% would be here, so 63% is going to be somewhere in between down here, so about 4 radians. So remember, radians are the distance that we would walk as if we were walking around the edge of this circle. All right, so the next thing we want to talk about is dimensional analysis. So dimensional analysis is a very, very powerful tool. So it's something that we do often without actually thinking about it, but when we write it down formally, it's going to give us a way to do a lot of things in a very nice way. So if I asked you how many minutes there were in 3 hours, what would you tell me? Probably that there's 180 minutes in 3 hours. And we got that by multiplying 60 by 3. But let's do this in a more formal fashion. So what we start with something we know to be true. Well, we know that 1 hour is equal to 60 minutes. Well, this is an equation. An equation is a statement that two things are equal. And we know that 1 hour is the same as or is equal to 60 minutes. So our fundamental rule of equation says that if I do something to one side of this equation, I have to do the same thing to the other side. So if I wish, I could divide both sides of this equation by 1 hour. And if I do that, my hours reduce out, and 1 divided by 1 is 1. So then this equation becomes 1 is equal to 60 minutes divided by 1 hour. So what we have on the right-hand side, we're going to call a unit fraction, or a conversion factor. And the reason we call that is 60 minutes divided by 1 hour is the same as 1. Well, 1 is the multiplicative identity. And that's just our fancy way of saying, well, what happens when you multiply something by 1? Well, what's 1 times 2? 2. What's 1 times 3? 3. 1 times x is x for every value of x. So when we multiply something by 1, it doesn't change. But this is the same as 1. So if I multiply something by 60 minutes divided by 1 hour, I'm not actually changing it. It's equal to exactly the same thing. So that's where this unit fraction or conversion factor comes from. So now if we go back to our original question, well, how many minutes are there in 3 hours? If I take 3 hours, I can write it as a fraction, just like anything, by putting it over 1. And if I multiply by my unit fraction, or if I multiply by 1, and multiplying something by 1 doesn't change it, that's the same as multiplying by 60 minutes divided by 1 hour. My hours reduce out. 3 times 60 is 180, and my units that are left are minutes. So this shows that 3 hours is exactly the same as 180 minutes. So we can do something similar with degrees and radians. So we know that one circle contains 360 degrees, and we know that the circumference of the unit circle is 2 pi radians. So if I divide both sides of this equation by 360 degrees, I get 360 degrees divided by 360 degrees is equal to 2 pi radians over 360 degrees. So on the left side, everything reduces out, and I get 1 is equal to, 2 goes into 360, 180 times, so pi radians all over 180 degrees. Similarly, if I take that same original equation, 360 degrees, I can divide both sides by 2 pi radians. So that would give me 360 degrees equals 2 pi radians. And I divide by 2 pi radians. And I divide by 2 pi radians. And again, 2 goes into 360 180 times. So 180 degrees divided by pi radians is equal to 1. And this gives me my two unit fractions, or conversion factors, to convert from degrees to radians, or from radians to degrees. So let's go back and look at this example. When I wanted to convert from hours to minutes in my unit fraction, since my hours were in the numerator, I needed the unit fraction or conversion factor that had hours in the denominator, so that the hours in the numerator would reduce out with the hours in the denominator, leaving me with the units of minutes. So in this first unit fraction, 1 equals pi radians over 180 degrees, that would convert from degrees to radians. And this second one would convert from radians to degrees. All right, so let's take a look at example number 2. So we wish to convert 5 pi over 4 radians to degrees. So I have 5 pi over 4 radians. I'm going to make it a fraction over 1, and I want to convert from radians to degrees. So I have radians in the top, so in my conversion factor, I'm going to need radians on the bottom, or the denominator. So I'm going to multiply by 180 degrees over pi radians. So now, when I do that, my radians reduce out, and the only degree units that are left are degrees, which is what I wanted. So now, my pi's reduce out, and I have 5/4 times 180. So 5/4 times 180. And that gives me 225 degrees. Or just 225 degrees. So that would be 5 pi over 4 radians is the same as 225 degrees. All right, so now it's your turn. I would like for you guys to convert 105 degrees into radians, and I would like you to do it using this conversion factor. All right, so to convert 105 degrees to radians, we would go 105 degrees, make it a fraction over 1, and then I would have 2 pi radians, or sorry, pi radians over 180 degrees. Then the degrees reduce out, and that would leave us with 105 pi over 180. And that reduces to 7 pi over 12 radians. All right, so now we need to talk a little bit about some conventions. So as I mentioned, radians are going to be our natural unit of measure. And because of that, we are pretty much going to assume by default that everything is in radians unless we are told explicitly otherwise. So here's our convention. When an angle is measured in radians, the word radians or rad is not written. That is, if an angle is given without units, we always assume that it's measured in radians. So if somebody gives you an angle but they don't put the degree symbol on it, then we assume that that is measured in radians by default. So from here on out, we will assume all measures are in radian, all angles are measured in radians, unless we are explicitly told otherwise. So the other part of that, then, is that we don't actually write the word rad or radians. So we're just not going to write it, and we're going to assume everything is in radians unless told otherwise. All right, the next thing we want to talk about is linear versus angular speed. So the best analogy that I can make between linear and angular speed is this. So angular speed is something measured in rotation, so how fast is something spinning around. So a good example to help us make this connection would be, imagine the wheel on your car. So the angular speed would be how fast is the wheel spinning around on your car, whereas your linear speed would be how fast is your car moving in a line on the ground. So angular speed is a rotation around a point, whereas linear speed is the speed that we're used to thinking about. So we have a relationship between linear and angular speed. So the linear speed v of a point, a distance r from the center of rotation, is given by v equals r, and then it looks like a w, but this is actually a Greek letter omega. And if you're curious, it's lowercase omega. So the Greek letter lowercase omega is the angular speed, and its units are always in radians per unit time. In the above formula, the units of distance for v and r must be the same, and this is the more important part. Omega has to be measured in radians. This formula is not valid. It doesn't work unless omega is given in terms of radians. So oftentimes we'll be given these things not in terms of radians, and we're going to have to do some conversions to get it into radians before we can use the formula. All right, so let's go ahead and take a look at a couple of examples. So, example 3, you recently changed your truck tires from a 30-inch diameter to a 34-inch diameter. If your speedometer indicates that you are driving 60 miles per hour, how fast is the truck really moving? So, if you change the diameter or the radius of the tire on your car, it's going to mess up your speedometer, because your car, the speedometer in your car measures how fast your tires are spinning. If you have a larger tire, your distance that you travel is going to be larger per one rotation. Hence, you will be going faster than what your speedometer says you are going. So if you change the diameter of your tire by 4 inches, how much is that going to change our speed? So we're going to need to use the formula that we were just talking about, v equals r omega, but we're going to have to do a few other things first before we can use that formula. So we have V, not with a highlighter, is equal to R times omega. And we're told if our speedometer indicates that we are driving 60 miles per hour, how fast are we really going? So the first thing we notice in our formula, we're given R, where R is the radius. We weren't given a radius. In this problem, we were given diameters. So we need to remember that the diameter D is equal to twice the radius. So in other words, that tells us that the radius is D divided by 2. So we're going to have two different radii. So our starting radius was 30-inch diameter. So if we have 30 inches and we divide it by 2, that's 15 inches. And our second radius is 34 inches divided by 2. So that's going to be a 17-inch radius. So we changed from a 15-inch radius to a 17-inch radius, and we want to know, well, how fast is our truck really moving? So when we have 60 miles per hour, that is a linear velocity. So we're going to have 60, and then our units are miles divided by hours is equal to, so that's our V. Our R is our radius, which was 15 inches times omega. So our speedometer, we need to figure out how many times our tires are rotating, or what is the angular velocity. So then solving this equation for omega, we divide by 15 inches, we divide by 15 inches. We have a fraction divided by a fraction, so we write it as a fraction over 1, and we get omega is equal to 60 miles divided by hours, and then we multiply by the reciprocal, which is going to be 1 over 15 inches, which gives us 60 miles divided by 15 hour inches. And that's going to reduce. 15 goes into 60 4 times, so we get 4 miles over hour inches. So that's our omega. And we now want to figure out our new velocity. So we're going to use our formula again. We have our linear velocity V is equal to R, but the radius of our tires is really 17 inches. So we have 17 inches times our omega, which is what we just found out. So 4 miles per hour inches. And we'll notice the inches reduce out as we would like. So 17 times 4 gives us 68 miles per hour. So then the actual speed of our truck would be 68 miles per hour. So if you change the radius of your tires from 15 inches to 17 inches, and your speedometer said you were going 60 miles per hour, you would really be going 68 miles per hour. All right. Let's take a look at our last example. So it says a water wheel has a radius of 10 feet if the water rotates if the water wheel rotates 14 times in 1 minute, what is the speed of the river in miles per hour? So once again, we're going to want to use the formula V equals R times omega. And our goal is we need to end up with our units. We want miles over hours, or miles per hour. We weren't given a lot of those things. So we want the units of V to be miles per hour. But if we look at what was given, we're told that the water wheel has a radius of 10 feet and that the water wheel rotates 14 times per 1 minute. So we're going to need to come up with some conversion factors and some unit fractions using dimensional analysis. So one that we may or may not know is that 1 mile is the same as 5,280 feet. This one we should know that there are 60 minutes in 1 hour. And lastly, 1 rotation is going to be the same as 2 pi radians, but since it's in radians, by convention we don't write radians, so 1 rotation is equal to 2 pi. So we need to convert our R and our omega into the appropriate units. So we start with our radius R. The radius of the water wheel is 10 feet, so we'll make it a fraction over 1. But our goal is miles per hour, so I need to convert feet into miles. So I have my conversion, or my equation right here, 1 mile equals 5,280 feet. Since I want to reduce feet out, feet need to go in the denominator. So I get 1 mile divided by 5,280 feet. And the feet reduce out. And 10 goes into 5,280, 528 times. So we get 1 mile over 528 is our radius. So 10 feet is 1/528th of a mile. And now we need to convert our omega. So omega this time was given as the water wheel rotates 14 times per 1 minute. So we have 14 rotations over 1 minute. But our goal is to end up in miles per hour. So we need to turn rotations into radians, and we need to turn minutes into hours. So to convert rotations, I have rotations in the numerator. So to reduce out rotations, in my conversion factor, rotations need to be in the denominator. So it's going to be 2 pi divided by 1 rotation. So then my rotations reduce out. And then I need to reduce out minutes into hours. But this time my minutes are in the denominator. So to reduce out my minutes need to be in the opposite part of the fraction, so in the numerator. So that's 60 minutes over 1 hour. And then my minutes reduce out. So now I multiply across the top, and I get 14 times 2 times 60 gives me 1,680. Pi, and then my units that are left in the top, there are none, because it's the pure units radians, divided by hours. So that tells me then that the angular velocity is 1,680 pi radians per hour. So now that I know r and I know omega, I can use my formula. V equals r times omega is going to be 1 mile over 528 times my omega, which is 1680 pi over hours. So then that gives me 1680 pi over 528, and then my units that are left are miles per hour, which is what I wanted. So that's my exact answer, but let's go ahead and get a decimal approximation. So I go 1680 pi over 528, and I get the following value. So then the linear speed of the river, V, would be approximately 10 miles per hour, because it's 9.9959, so I'm going to round that to about 10 miles per hour.